I've spent most of my life staring at faint specks of light, chasing whispers from the universe that most people never notice. To the outside world, astronomy sounds like a profession of grandeur, giant telescopes, galaxies, and cosmic revelations. But the truth is, most nights are silent. Hours pass in dim rooms filled with the hum of cooling fans, the clicking of keyboards, and the faint mechanical whir of observatory domes shifting position. That night was no different. I was at the Pan-STARRS facility in Hawaii, surrounded by screens that glowed with long-exposure images of the sky. My colleagues had already gone quiet, their tired faces bathed in pale light, the kind of stillness that makes you forget how late it is. The world outside was asleep, and it felt like only the stars were awake with me. I was scanning a batch of data, frames taken automatically by the telescope, dots of light, some sharp, some blurry, all cataloged by software that would eventually filter out the known stars, galaxies, and asteroids. Most of what I looked at were false positives, cosmic rays, streaks, smudges, noise. But in one frame, near the constellation Ursa Major, there was something different, a faint greenish blur. At first, I thought it was an imaging artifact, the kind of thing you delete without a second thought. But then I compared it to the next frame. The blur had shifted. I leaned forward, heart beating a little faster. Things don't shift like that unless they're moving. And if they're moving, they're close. I ran a quick orbital calculation. Numbers appeared on my screen, the kind of raw data I'd memorized after years of study. Speed, trajectory, inclination. At first, it didn't make sense. My brow furrowed. I rechecked, recalibrated, fed the coordinates through again. Same result. It wasn't bound to our solar system. That blur, faint, fragile, almost lost in the digital noise, wasn't just another comet from the Oort cloud. It wasn't from here at all. I sat back in my chair, staring at the data as if it might blink away if I looked too hard. Interstellar. The word itself felt unreal, like something out of textbooks and speculative talks at conferences where people argued about Oumuamua, the first interstellar object we had detected just a few years prior. We'd told ourselves we might not see another for decades, maybe centuries. And yet, here it was. I whispered to myself without meaning to, "My God, it's another one." The room suddenly felt alive, though no one else had spoken yet. I nudged the colleague next to me, half afraid I was imagining it. "Hey, look at this. Do you see it?" He leaned in, groggy but curious. His eyes scanned the frames, then widened. "That's moving fast." "Not just fast," I said, voice trembling. "It's not from here." Within minutes, the quiet observatory turned electric. People who had been dozing off now leaned over keyboards, calling up additional data. We requested confirmation images from other observatories. Emails shot out, phones buzzed. A chain reaction of urgency spread from our small room to the wider network of astronomers across the globe. We had found something the universe rarely gives away: a visitor. The name came later, after the calculations were confirmed: C/2019Y4 Atlas, a comet, a green wanderer from beyond the sun's reach, plunging into our system on a one-way trip. But in that first hour, before the press releases, before the news headlines, it was just us and the faint smudge of light that had traveled for millions of years through the cold void before appearing on our screens. I remember staring at it, forgetting to blink. My hands shook. It wasn't fear exactly, but something stranger, heavier, a kind of reverence. How many stars had this fragment passed? What gravitational giants had bent its path? What ancient collisions had launched it across the interstellar gulf to end here, at the edge of human sight? And then another thought struck me. What secrets could it carry? Comets are time capsules, frozen relics from the birth of solar systems. If this one wasn't born under our sun, then it carried the chemistry of another star, another cradle of worlds, dust and ice older than Earth itself. I could feel the weight of it, humanity's hunger to touch the unknown, to learn if we were alone, to understand how far life's ingredients might travel. For the first time in years, my work didn't feel like data points and noise. It felt like touching the edge of infinity. The next 48 hours changed everything. What started as whispered conversations between a handful of astronomers became front-page news across the globe. I watched from my office as the story spread like wildfire through social media, scientific journals, and news outlets. "Interstellar comet discovered," the headline screamed. "Visitor from another star system heading toward Earth." My phone hadn't stopped ringing. Reporters wanted quotes. Colleagues from universities I'd forgotten I knew were reaching out. My inbox overflowed with interview requests, collaboration proposals, and messages from amateur astronomers asking how they could help track our cosmic visitor. But it wasn't just the scientific community that was stirring. The public reaction was unlike anything I'd witnessed before. People were sharing telescope images, artistic renderings, and wild theories about what the comet might contain. Some called it a sign. Others feared it was dangerous. Most were simply captivated by the romance of it all. A messenger from the stars carrying secrets from worlds we'd never seen. The debates within the scientific community were just as intense. During a hastily organized video conference with astronomers from ESO, NASA, and other observatories worldwide, the discussions grew heated. "It's just a dirty snowball," insisted Dr. Martinez from the Madrid Deep Space Network. "Frozen gases and rocky debris. The fact that it's interstellar doesn't change the basic physics." But Dr. Chen from Beijing disagreed. "We can't assume its composition matches comets from our solar system. This object formed around a different star, under different conditions. Its chemistry could be completely alien to us." I found myself caught between skepticism and wonder. The scientist in me agreed with Martinez. Comets are comets, regardless of their origin. But the dreamer in me whispered that this was different. This was special. What if it's carrying organic compounds we've never seen before? I ventured during the call. What if it holds clues about how life might form in other solar systems? Dr. Patel from the Indian Space Research Organization spoke up. "That's exactly why we need to study it thoroughly before it's gone forever." And that was the thing that haunted me most during those early days. Atlas wasn't going to stick around. Unlike planets or moons that we could observe for years, our interstellar visitor was on a hyperbolic trajectory, a one-way ticket through our solar system. We had months, maybe a year at most, before it would disappear back into the cosmic dark, taking its secrets with it. The pressure was immense. Every night of clear sky was precious. Every observation could be our last chance to understand something fundamental about the universe beyond our solar system. The global collaboration that emerged around ATLAS was extraordinary. Observatories on every continent were tracking it, sharing data, coordinating observations to maximize our coverage. Amateur astronomers with backyard telescopes were contributing images. Even radio telescopes were listening for any signals. The speculation reached a fever pitch when the first spectroscopic analysis came back. The comet's coma showed unusual emission lines. There were complex organic molecules, carbon chains longer than we typically saw in solar system comets, and isotope ratios that didn't quite match what we knew from local objects. "It's like looking at the chemistry of a star system that formed under different conditions than ours," I explained to my wife Sarah over dinner. "Different metallicity, maybe different stellar winds during its formation. It's a sample of cosmic evolution we've never had access to before." She smiled, recognizing the excitement in my voice that I couldn't hide. "So it really is special." "It might be more special than we imagined." A graduate student named Alex had been running simulations of how objects like ATLAS could survive the journey between star systems. His results were startling. For a comet to maintain its structural integrity during an interstellar journey, it needs to be protected from cosmic radiation and the interstellar medium, he explained. But the model suggests that only objects with specific compositions and sizes could make the trip intact. The implications hit me immediately. You're saying Atlas represents a very select population. Only certain types of comets can become interstellar travelers. Exactly. They're natural selection in action on a galactic scale. We weren't just looking at a random chunk of ice and rock. We were looking at a survivor, something that had endured the harshest environment in the galaxy for potentially millions of years and emerged to tell its story. 3 months after discovery, ATLAS had transformed from a faint smudge on a computer screen into something magnificent. I stood outside the observatory at 3 a.m., no longer needing a telescope to see our interstellar visitor. It hung in the constellation Ursa Major like a ghostly sword, its tail stretching nearly 10 degrees across the sky, 20 times the width of the full moon. The comet's coma had grown to enormous proportions, a green-tinted cloud of vaporizing ice and dust. "Have you ever seen anything like it?" asked Dr. Reeves, one of the graduate students who'd been pulling all-nighters with me. I shook my head slowly. Hale-Bopp was spectacular, but this is different. This is older. This has seen things we can't imagine. The spectroscopic data we'd been collecting told an increasingly fascinating story. As Atlas approached perihelion, the heat was causing its nucleus to outgas at tremendous rates, but what was coming off wasn't just water vapor and carbon dioxide like we'd expect from a typical comet. The molecular signatures were extraordinary. Complex organic compounds were streaming away from the nucleus. Amino acid precursors, nucleotide bases, long-chain carbon molecules that formed the building blocks of life as we knew it. Not life itself, but the chemistry that life required. "It's like a factory," I told the international team during our weekly conference call. Atlas is manufacturing and releasing exactly the kind of molecules that could seed a young planet with the ingredients for biology. Dr. Yamamoto from JAXA leaned forward on the video screen. "Are you suggesting panspermia? That life might travel between star systems on objects like this?" The word hung in the digital air between us. Panspermia, the hypothesis that life exists throughout the universe distributed by meteoroids, asteroids, comets, and planetoids. Atlas was providing the first direct evidence that it might actually be possible. "I'm just reporting what we're seeing," I replied carefully. "This comet is carrying a pharmacy of prebiotic molecules. If something like Atlas impacted a young, water-rich planet..." I didn't need to finish the sentence. Everyone understood the implications. But even as the scientific discoveries mounted, I was grappling with something more personal. The closer Atlas came to the Sun, the more unstable it became. High-resolution images from the Hubble Space Telescope showed cracks forming across its nucleus. Chunks of material were breaking away, creating subsidiary tails. Atlas was dying. Watching this ancient traveler slowly disintegrate under the sun's heat felt like losing something irreplaceable. Every fragment that broke away was a piece of another star system, lost forever. Sarah found me on the back porch one evening, staring up at the comet with my binoculars. "You look like you're mourning," she said. "Maybe I am," I admitted. "This thing has been traveling for longer than human civilization has existed. It survived the cold and radiation of interstellar space, avoided being captured by other star systems. It made it all the way here, only to be destroyed by our sun." "But isn't that why it came here?" she asked gently. "To give us its story before it dies?" Her words hit me harder than I expected. Maybe this wasn't tragedy, but fulfillment. Atlas had carried its message across the galaxy for millions of years, and now it was finally delivering it, written in spectral lines and molecular signatures that only a species with our level of technology could read. The fragmentation accelerated dramatically as ATLAS reached its closest approach to the Sun. What had been a single nucleus became a string of glowing fragments, each following the same orbital path, but spread out like pearls on a cosmic necklace. "It's the most beautiful thing I've ever seen," whispered Maria, one of the postdocs, "and the saddest." The scientific data flowing in was unprecedented. Each fragment had a slightly different composition, giving us insight into the internal structure of our interstellar visitor. Some pieces were rich in water ice, others heavy with rocky debris. A few fragments showed unusual mineral signatures that didn't match anything we'd seen in solar system comets. Fragment C3 is showing crystalline structures that could only form under very specific temperature and pressure conditions, Alex reported excitedly. "We're seeing minerals that crystallized in an alien stellar nebula." We weren't just studying a comet. We were performing an autopsy on a piece of another star system, examining the fossilized remains of processes that had occurred around a different sun billions of years ago. During what would be our last good observation night, I was alone in the observatory when one of the larger fragments brightened dramatically. In just a few minutes, it went from a faint smudge to a brilliant star-like object, and I could actually see the expanding cloud of debris with my own eyes. Somewhere in that expanding cloud were molecules that had formed around a young star billions of years ago. Dust grains forged in stellar nucleosynthesis. Water ice that had condensed in an alien solar system and then wandered the galaxy for eons. And now it was all dispersing into our solar system, mixing with the local interplanetary medium, becoming part of the cosmic ecosystem that had given birth to Earth. We're watching two star systems meet, I realized. Atlas isn't just visiting our solar system, it's merging with it. By late May, ATLAS had become a ghost of its former self. What had once been a magnificent tail stretching across 10 degrees of sky was now a faint, dispersed cloud barely visible even through our most powerful telescopes. The nucleus had fragmented into dozens of small pieces, each following the same orbit, but spread out over thousands of kilometers like a cosmic funeral procession. The data analysis phase had begun in earnest. My desk was buried under printouts of spectrograms, orbital calculations, and theoretical models. Every computer in our department was running simulations, trying to reconstruct ATLAS's billion-year journey backward through time and space. "Look at this," Alex said, bursting into my office with his laptop. He'd been working 18-hour days, trying to trace the comet's path through the galaxy using stellar motion models. He pulled up a three-dimensional simulation of stellar movements over the past few million years. Stars drifted across the screen like fireflies, their paths bent by gravitational interactions and galactic rotation. "I've been running backward integrations," he explained excitedly, taking Atlas's current trajectory and rolling back the clock. The simulation showed a bright dot, representing ATLAS, tracing a complex path through space as the years rolled backward. 10,000 years, 100,000, a million. At roughly 3.2 million years in the past, the simulation showed Atlas passing remarkably close to a familiar star system. "Wolf 359, I breathed, recognizing the distinctive orbital configuration, a nearby red dwarf star system, only about 7.9 light-years from Earth. "It's our best candidate for ATLAS's origin," Alex said. "The timing works, the trajectory fits, and Wolf 359 is old enough to have formed planetary systems with debris disks that could produce comets." Wolf 359 was practically our next-door neighbor in galactic terms. Atlas hadn't come from some impossibly distant realm. It had originated in our local stellar neighborhood. "A message from the neighbors," I murmured. The implications were staggering. Atlas represented direct material exchange between star systems in our local galactic neighborhood. We weren't isolated islands of matter floating in empty space. We were part of a dynamic network where planets, comets, and debris regularly traveled between nearby stars. The fragmentation had scattered comet material across a huge volume of space, creating a debris stream, a river of dust and ice particles following the same orbital path. Dr. Martinez from Madrid had been modeling the evolution of this debris stream. Most of the material will continue on the hyperbolic trajectory and head back out into interstellar space. But some of the smaller particles, dust grains, organic molecules, they could be captured by gravitational interactions or solar radiation pressure. The implications were mind-boggling. Particles from ATLAS, molecules forged around an alien star, might eventually rain down on Earth, Mars, Venus, all the worlds of our solar system. Our interstellar visitor would become part of us, part of our cosmic environment, forever. We need to follow up, I said suddenly. We need to track the debris stream, model where the particles end up, maybe even try to collect samples if any reach Earth. Dr. Patel surprised me. ISRO would be interested in such a collaboration. The astrobiological implications are too important to ignore. One by one, other team members voiced their support. ESA, NASA, even the Chinese National Space Administration expressed willingness to contribute resources to a long-term ATLAS follow-up program. The final weeks of visible ATLAS were bittersweet. Each night, the fragments grew fainter. Photography enthusiasts around the world were capturing what they knew might be the last images of our interstellar visitor. It's like watching a friend move away, Maria confided. You know you might never see them again. Perhaps the most poignant moment came from the Arecibo Observatory. They'd been monitoring ATLAS throughout its approach and had something special to share. We've been recording the radio signatures from the comet's interaction with the solar wind, explained Dr. Santos. As ATLAS fragments and disperses, these electromagnetic emissions are creating what can only be described as a cosmic song, the death song of an interstellar wanderer. He played the audio for us, radio waves converted to sound frequencies. It was haunting, a complex mixture of tones and harmonics that rose and fell like a vast, otherworldly choir. It's beautiful, Sarah whispered. As we listened to Atlas's radio swan song, I felt a profound sense of closure mixed with anticipation. The comet was gone, but its legacy would endure. The isotope analysis results had finally come in from laboratories around the world. Every fragment showed the same signature: deuterium ratios, oxygen isotope patterns, and trace element compositions that were subtly but definitively different from solar system material. We now had irrefutable proof that ATLAS had formed around a different star. This is our Rosetta Stone for interstellar chemistry, Dr. Chen announced. For the first time, we have detailed compositional data from another stellar system. For me, the most meaningful discovery was simpler: the confirmation that we lived in a galaxy where matter flowed freely between star systems, where the ingredients for worlds and life traveled regularly across interstellar distances, where no solar system was truly isolated. On the final night of our observation program, the entire team gathered at the observatory. We pointed the telescope toward Ursa Major one last time, searching the same patch of sky where we'd first spotted that faint greenish blur 9 months earlier. The field was empty now, showing only the familiar pattern of background stars. "Farewell, traveler," I whispered, the same words I'd spoken that first night, but with a completely different understanding of what they meant. Atlas was gone, but it had taught us that the universe was full of travelers, that matter and energy flowed constantly between the stars, that we were part of a galactic ecosystem that had been operating for billions of years. 6 months after Atlas faded from view, I received an email that would change everything again. Dr. Kenji Nakamura from the Japanese Aerospace Exploration Agency had been monitoring unusual dust particles entering Earth's atmosphere, microscopic grains with isotopic ratios that didn't match typical solar system material. When they traced the orbital mechanics backward, the particles' paths intersected perfectly with ATLAS's debris stream. Pieces of ATLAS were falling to Earth. The first time I looked at an Atlas particle through an electron microscope, I forgot to breathe. Smaller than a human cell, but embedded within that tiny grain were minerals I'd never seen before. Crystal structures that had formed under conditions completely unlike anything in our solar system. We were literally holding alien geology in our hands. The organic chemistry results were even more astounding. Mass spectrometry revealed complete molecular chains that looked remarkably similar to the building blocks of terrestrial life. Not identical. The isotopic ratios were subtly different, but close enough to suggest that the chemistry of life might be universal. I was walking across campus one evening when a student stopped me. "Professor Thompson," she said, "do you really think there are others out there heading toward our solar system right now?" I paused, looking up at the stars. Absolutely. Based on what we've learned, there are probably dozens of interstellar objects passing through our solar system at any given time. Most are too small or too dark for us to detect, but they're there. Her eyes widened. So we're constantly being visited by travelers from other star systems? More than that, I said, we're constantly exchanging material with the rest of the galaxy. Every year, tons of interstellar dust enters our solar system. The galaxy isn't empty space with isolated star systems. It's more like a vast ocean with currents of matter flowing between every shore. She stood quietly for a moment. Then, "That's the most beautiful thing I've ever heard." As she walked away, I realized she'd summed up exactly what ATLAS had taught me. Not just that interstellar visitors exist, but that we're part of something infinitely larger and more connected than we'd ever imagined. Objects like ATLAS pass through our solar system several times per decade. Most go unnoticed, but they're there, carrying stories from distant stellar neighborhoods, broadcasting that matter flows freely through the galaxy. Last month, another email made my heart race. An automated survey telescope in Chile had detected a new object with an unusual orbit. Preliminary calculations suggested it might be another interstellar visitor. I'm older now, grayer with lines around my eyes from squinting at computer screens in dark observatories, but the excitement is exactly the same as that night when we first spotted ATLAS. Atlas taught us that we're not alone, not in the sense of finding alien intelligence, but in discovering we're intimately connected to the broader galaxy. The carbon in our bodies, the water in our oceans, the complex molecules that make life possible. They've all been traveling between the stars for eons. The research program that grew from ATLAS particle analysis has consumed years of my life. We've published papers on interstellar dust dynamics, prebiotic chemistry, isotopic signatures of extrasolar material. But beyond the publications, ATLAS changed something fundamental about how I view the universe. We now know the galaxy is full of wanderers, ancient comets, asteroid fragments, maybe even pieces of shattered planets, all traveling between stars and carrying stories we're learning to read. Sarah found me on the back porch recently, staring at the sky with that familiar expression. "Another traveler?" she asked, settling beside me. I nodded, pointing toward the constellation where our newest visitor was still too faint to see. "Another story waiting to be told?" She smiled, taking my hand in the comfortable silence that had grown between us over decades of shared wonder. "Welcome, traveler," she whispered to the stars. An email arrived yesterday from that teenager in Tokyo, now finishing her astronomy degree. "Professor Thompson, I'm starting graduate school next year. I want to study interstellar objects. Atlas showed me that the universe is full of connections we're only beginning to understand." Reading her message, I understood ATLAS's most important legacy. Not the scientific data or insights about chemistry, but the generation of young people who looked up at our cosmic visitor and felt their horizons expand. The universe, I've learned, is not a collection of isolated islands, but a vast, interconnected web where matter and energy flow constantly between the stars. Every atom in our bodies was once part of this cosmic circulation system. Atlas was our first direct encounter with this reality, but it won't be our last. Somewhere in the cosmic dark, Other ancient wanderers continue their billion-year journeys toward our waiting telescopes, carrying secrets we haven't even thought to ask about yet. We just have to keep watching, keep listening, keep reaching out with our instruments and our curiosity toward the infinite mystery that surrounds us. And when we find them, we have to remember to say hello. The universe is full of travelers. We just have to learn how to see them.